This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Topic 10 of Week 4. Hazen-Williams head loss, the empirical shortcut every water distribution and fire protection problem leans on. No Reynolds number, no Moody chart, just one roughness coefficient called C. We'll build the formula exactly as the handbook prints it, decode its unit mix and its per-foot output, work an example, and lay out when Hazen-Williams is the right tool and when you must fall back to Darcy-Weisbach. First, why this formula exists. Darcy-Weisbach is exact, but it makes you find a friction factor, a Reynolds number, and the Moody chart. For ordinary water in a distribution main or fire loop, that's more work than the problem deserves. Hazen-Williams replaces all of it with one empirical roughness coefficient, C. No Reynolds number. C already bundles the turbulent friction. No Moody chart. Head loss falls out of one closed-form equation. The catch is in the design. Water only, calibrated for normal temperatures. You trade rigor for speed, and it only pays off inside the calibration range. The printed equation, H sub F equals 10.44 times Q to the 1.85 divided by C to the 1.85 times D to the 4.87. The units are locked, flow in GPM, diameter in inches, and what comes out is feet of head loss per foot of pipe. Multiply by the run length for the total. Diameter in inches is the trap. At the 4.87 power, a feet slip is off by a factor of 180,000. Now, the coefficient that drives everything, C. Don't memorize this table, find it. Plastic is the smoothest on it at 150. New welded steel, the one you'll see most, is 120, and the values run down from there as pipe ages. Higher C, smoother pipe, less head loss. And a key difference from Darcy-Weisbach, C already folds in aging and corrosion, so unlike a fixed roughness epsilon, it changes over the system's life. Because C appears raised to that same high exponent in the denominator, having it more than triples the head loss. Note where the table stops. 100. A badly corroded old main falls below the table, and that's judgment, not a lookup. Old pipe problems live or die on picking the aged C. Right under it, the same page prints a pressure form. P equals 4.52 Q to the 1.85 over the same denominator. PSI per foot of pipe times the run length for the total. 1 PSI of water is 2.307 feet of head, so the two forms check each other for free. And if a problem wants velocity, there's no printed velocity form. Get Q from the head loss equation, then V is Q over A. The variable table, H sub F, comes out of the printed equation in feet per foot of pipe. The run length is your multiplier at the end. Flow in GPM, diameter in inches, and C from the material table. Matching the pipe's age is the only judgment call on the slide. The worked problem. 1,000 feet of new 8-inch steel main at 500 GPM. Find the head loss. New steel gives a C of 120 from the table. Plan, confirm the units, apply the printed equation for the per foot loss, then multiply by the run. Build the three powers. Q to the 1.85 is about 98,400. C to the 1.85, about 7,000. D to the 4.87, about 25,000. Divide 0.00585 feet per foot of pipe. Times the 1,000-foot run, 5.85 feet of head loss. So, which formula? The split is clean. Reach for Hazen-Williams when the fluid is water at normal temperature. Water distribution, fire protection, and above all, when the problem hands you a C coefficient. Reach for Darcy-Weisbach when the fluid is anything but water, when viscosity matters at high or low temperature, when you're given a roughness or a friction factor, or when you need Reynolds-based rigor. The fastest tell is what the problem gives you. A C points to Hazen-Williams. A roughness, viscosity, or Reynolds number points to Darcy-Weisbach. The deep reason, Hazen-Williams has no viscosity term, which is exactly why it can't touch oil, air, or off-temperature water. 4 traps. 1. Diameter goes in as inches, never feet. The 4.87 power makes that slip enormous. 2. The printed loss is per foot of pipe. Multiply by the run or you're 1,000 times off. 3. Water only. For oil or air, switch to Darcy-Weisbach. 4. Match C to the pipe's age. A new pipe value flatters a corroded main. Bookmark the one page that has it all. The head loss form in feet per foot of pipe, the pressure form in PSI per foot, and the C table. Multiply either by the run length. If the fluid isn't water, or they hand you a roughness or friction factor, fall back to Darcy-Weisbach, one page earlier. That's Hazen-Williams, the printed head form and pressure form, both per foot of pipe, times the run length. Guard the inches and the times L, match C to the pipe's age, and hand anything that isn't water to Darcy-Weisbach. Next topic, we keep building the Week 4 toolkit.
The full study guide, with every equation and common exam trap, is free at peprepengine.com. Link in the description. Machine design, HVAC, structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.